the topic is discontinuous functions. We already talked a little bit about those functions. So the definition that we're using is that d of f is going to be the set of discontinuities of f. So it includes all points at which some function from, say, the space M to R is discontinuous. So let's begin with obvious example. So example A, if f is monotone, then we have seen that the discontinuities, and by f monotone, of course, I'm talking about R. So the set of discontinuities from your assignment 1 is at most countable, right? And such discontinuities are all jump discontinuities. Now, on the other hand, conversely, any countable set is a set of discontinuities for some function f, and that's what we have constructed. So the example of that f would be, say, if I want to say that df is the set of points x1, x2, xn onwards. So just some sort of list of elements that can be arranged with the integers. I will then just take x1 and group it with epsilon 1, x2 group it with epsilon 2, and so on and so forth. So xn is grouped with epsilon sub n. And the way we define this function is, for example, f of x is the summation over on such that xn is less than x, and we are summing epsilon sub n. So that's the example that we have already covered. Now, this function has this particular set of countably many elements as its discontinuity set. And this function is monotone. It's in particular increasing. So example B. So there are functions f from R to R, where the discontinuity of f is equal to q. Now, one example of it is, again, you can just list q as the x1, x2, xn. And this would be then a function that is monotonically increasing and discontinuous over q. So a few of you, and actually this is correct, the example that you had to do for assignment 1, you could actually draw this as a sequence of step functions. And many of you, that's how you explain this discontinuity. This is nice, except that if I list the sequence to be all the rational numbers, that will not be possible to draw it as a step function, right? It will be just way too discontinuous for this drawing to work. The rational numbers are dense on the number line. So then what you do is you should have analytic proof. But aside from this function, there is one example which is called the popcorn function. You can actually find it also in Spivak. He uses it as an example for integration theory. So popcorn function is, in fact, discontinuous only at the rational numbers. And here is the definition that we can make over all of R. Popcorn function f from R to R given by f of x can be written as f of n plus y and here y is a number bigger than or equal to 0 and less than 1, right? So I can write any real number as an integer and plus some element from R that is only in between 0 and 1. And what it will be? It will be then just the same as f of y, where then now f of y is between 0 and 1, and it's defined to be 1 over q if y can be written in reduced form as p over q. Okay, that's reduced form. So reduced form meaning that p and q are relatively prime. They are relatively prime integers. And otherwise it is 0 if y belongs to r minus q. So if it's not, if it's an irrational number, then the popcorn function gives 0. So first question, y continuous at each irrational number. Why is this function continuous at the irrationals? Can you see it?
Because it's 0 for all the irrational.
It is 0 for all irrational numbers, but it is
rationals going to the irrationals and it's going to be a null sequence.
by a null sequence. You mean what?
Converges to 0.
The sequence will. So you mean the denominator will grow, and that's true, and that's true. And the way to see this is just pick epsilon. Epsilon bigger than 0, and 1 over q smaller than epsilon. So make sure that 1 over q is smaller than epsilon. Then what you will do is, if I have this x, which is an irrational number, so x is in r minus q, then what I can do is I can select a thin enough interval so that in this thin interval no rationals of the form P over R, where R is smaller than Q. Okay, so that means that every rational number living in this interval has denominator that is bigger than q. So that means that f applied to this interval, I'm just drawing it, right? F applied to this interval, it is going to be its supremum is going to be something of the form 1 over q, which is smaller than epsilon. So all the numbers in here are mapped to within epsilon away from 0. And this point, x, it's mapped into 0 because it's irrational. Okay? So that's basically just a drawing explanation. You can just write it out if you want to. It's a drawing explanation why at every irrational number the function is continuous. Notice it's, by the way, periodic with period 1. Right? So it's like if you add 1 to x, you just get the same as f of x. Really, it's enough to define it only in the interval from 0, 1. It is equally simple to verify that it is discontinuous at the rational numbers. So it is equally simple, I think maybe even simpler, to verify that f is discontinuous at each rational number. All right. So that is the popcorn function, and its set of discontinuities is Q. Are there functions whose set of discontinuities are the reals?
No.
So dg, can it be equal to the real number? In other words, what I'm asking?
G doesn't have to be monotonic.
Well, it doesn't have to be monotonic. Sure, if it's monotonic, then the answer is no.
Yeah.
Absolutely, right? If it's monotonic, the answer is no. But if it's not monotonic, what could be the answer? Could be yes. Do you have examples? So this is asking, can a function be discontinuous everywhere?
Just like 0 if it's rational, 1 if it's irrational.
Yes, which is the characteristic function. So that's the standard example. So g equal to the characteristic function of q. And that means that g of x is equal to 1 if x is rational, and it's 0 if x is irrational. So this function has the property that d of g is equal to r. It's easy to verify. So what we're about to see is one part of a major theorem. And what this theorem is telling us is that the set of discontinuities of a function is always an F sigma set. It's always a union of countably many closed sets. Where, of course, in this union, you can make it finitely many closed sets by making the remainder just the empty set. Empty set is closed. Just if you union with the empty set, you don't change it. So first of all, we need to have a characterization of the discontinuities of F. So we would say that A belongs to the set of discontinuities of F. Here F is, let's take it as a function from the metric space M into R. And then we say that A belongs to the set of discontinuities of F if what happens? If there is epsilon bigger than 0, such that absolute value of f of x minus f of a is always bigger than or equal to epsilon for every delta bigger than 0. Right? That's just basically the reverse of the delta epsilon definition. It fails. You cannot construct a delta as a function of epsilon and make this arbitrarily small. Pictorially, you can imagine having, this is your ball of radius delta centered at A, and if you build this water gun, and you feed everything into this function, how do you verify the discontinuity? You feed all this stream into this function, and as you do this, you are going to shrink. You're going to shrink the ball into the point A. Right? So you are shrinking this ball, and you are feeding this water current into this gun. And you're seeing where this gun is spraying. So the gun is going to be spraying into the point f of A and into other points. What happens to the stream? The stream never gets narrow around f of A. Right? There is always going to be some element x in this ball that is going to be mapped somewhere else. So that means in particular that the diameter does not shrink. So that happens if and only if the diameter as delta goes to 0 of f applied to the ball of radius delta centered at A is going to be always bigger than or equal to epsilon. Do you see that? Diameter of the set, if it shrinks, that means that the limit exists. If it shrinks towards f of A, that means this limit is f of A. But the diameter here will not shrink because there is going to be always something that is mapped somewhere else outside of this ball of radius epsilon. No matter how much this is squished, how much small you select your open ball, the cannon is gonna not have all of its current. All these atoms are not gonna fly near f of A. Some are gonna fly far. So this is our characteristic. So we define the oscillation at the point A. So the oscillation of f at A to be limit as delta goes to 0, diameter f of B delta centered at A. Okay? So the oscillation is basically measuring how discontinuous is the function at a particular point. Does it make sense? And then the set of all discontinuities of f is going to be the collection of all A such that the oscillation is bigger than 0. So very important, crucial point here. Do you understand what oscillation is measuring? So when I think that is the function continuous or not, what do? I am going to take this ball centered at A. I'm going to select some delta for it. And I'm going to measure the diameter. So you see all those points, the diameter is just basically how wide is the stream. So the diameter is I just measure when I feed those points into the gun, into F. The gun is F. And it's going to spray each atom of this open ball into an atom on this vertical wall. Right? Then I'm looking at the stream. If the stream gets arbitrarily narrow, that means that the diameter here shrinks to 0. That's continuity. What's not continuity? If the diameter of the stream does not shrink to 0. And that is just what this is expressing. Oscillation is how much is the diameter not shrinking to 0. The bigger the oscillation, the less continuous the function. Understandable, right? Good.
At a point A?
At a point A, right? So I can quantify the discontinuity to say, well, this is a much worse discontinuity if this epsilon is bigger, right? If it shrinks to 0, you see the stream should shrink to f of A clearly, because f of A is one of the points in the set, the diameter that I'm calculating. F of A is going to be part of it. So if everything shrinks to 0, that means that the limit is f of A. If it does not shrink to 0, then how badly doesn't it shrink to 0? The bigger the epsilon, the worse is the discontinuity. Note that it matters, I guess, qualitatively. A function is discontinuous if this is not 0. Oscillation will always be positive, right? Another way to measure oscillation, just so that you are clear, what we do is we take the supremum over delta of f of x minus f of y, where delta is bigger than, I should write it like this, delta bigger than the distance of x to y. Okay, so that's just the same thing as taking the supremum sorry, as taking the diameter of f of the ball of radius delta centered at A. Diameter, no limit. Limit is when we are measuring oscillation, because it's not enough to just, you see, it should not be necessarily 0 for any delta. It should be 0 if delta is made smaller and smaller and smaller. The limit as delta goes to 0 of the diameter should shrink. So as I shrink the open ball, the diameter of the stain should shrink to 0. That's really what should happen, right? So open ball is the current water. The stream is once it has impacted the wall. I want to measure if the diameter of the stain is shrinking to 0. Good? All right. So now we are able to state the theorem. Theorem is and we can state it already for all metric space functions. So if f from MD to R then the set of discontinuities of f is equal to the infinite union of Fn and goes from 1 to infinity, where Fn is a closed set. So this means that d of f is an f sigma set. So it's an example of a Borel set where what you're doing is you're taking unions of closed sets. So remember f for Fermat, sigma for sum. So let's prove this theorem. Proof. So we know that d of f is the set of all points A such that the oscillation of f at A is bigger than 0. Now if the oscillation is bigger than 0, then I can write this as the union of A such that the oscillation is bigger than 1 over n. Okay, so very important, do you agree that both sets are the same? If I have oscillation that is bigger than 0, then it's going to be necessarily bigger than some one element of the form 1 over n. Or any other sequence, in fact, that goes to 0. I just picked the harmonic sequence because it goes to 0 monotonically, right? Monotonically decreasing sequence. So for example, the oscillation, if it's very, very bad, it's bigger than 1. If it's less bad, it's bigger than 1/2. If it's less bad, it's bigger than 1/3. Right? So, but basically those sets, by the way, as you can see, they are increasing. The set that contains all A that are, so in fact, in this argument, I can choose this to happen. So I can make it a sequence of increasing sets. So we have it. Now the question is, how do I know those are closed sets? All right. So what are properties of closed sets that we can use? if this set is closed, then in particular, if I have a limit point for that set, so if x is a limit point of Fn, enough to show x is an element of Fn. So it has to eat all its limit points. Well, what we can do is we can select any ball of radius delta centered at x. So if delta is bigger than 0, pick any ball of radius delta centered at x. Now, this ball intersection Fn is not empty. So there is A belonging to the ball radius delta centered at x, such that the oscillation of f at A is bigger than or equal to 1 over n. Correct? So let's draw what we just verified. So here is my x, and here is where I picked A. Now what can I do? I can then select a ball of radius r that is very small and centered at A. So this ball is going to have radius r, whereas this is the ball of radius delta. Now, what do you know about the oscillation in the ball of radius r? What do you know about the diameter of the image under f of this ball? So you know that diameter of f ball of radius a centered at A. What do you know about this diameter? I assume that oscillation at A is bigger than 1 over n. What do I know about the diameter here? This red drawing that I drew here.
Greater than 0?
In particular, not just greater than 0. Think about it, right? So the diameter, when I push r closer to 0, right? What this is saying is push r close to 0. So here is a point A, it's inside, you see, there is intersection. X is a limit point of Fn, which means no matter how small I pick delta, there is going to be an element A that is common to Fn and this set. This element A has oscillations bigger than or equal to 1 over n. That means what? That means that if I pick A inside of this open ball, choose any radius r smaller than small enough so that it's fully contained in the ball of radius delta centered at x. What can I say about the diameter of this ball? Diameter of f of this ball.
It's greater than 1 over n.
It's greater than 1 over n. Now diameter of the ball only decreases. So this is less than or equal to the diameter of f applied to the ball of radius delta centered at x. Okay? And this is true for all delta. That's very important, that it's true for all delta bigger than 0. And that implies that limit as delta goes to 0 of the ball of radius delta around x will be bigger than or equal to 1 over n. And this is just the oscillation of f at x. So it's also of the same type. So that implies that x belongs to the ball, sorry, that x belongs to f sub n. The proof is complete. Okay? On the exam, one question I consider is, for example, I give you any closed set. Can that closed set be, can that closed set that I give you be a set of discontinuities for some function? Create a function, if so. Or show that there might be closed sets that this does not happen. So that's one exam question. I like it. All right. No questions about this? All clear? All right. Then next topic is Baire Category Theorem. So the main question is, we know that the f is equal to f sigma set. What sets can be written as f sigma? So that's one question that you can have. Naturally, one even more obvious question is it true that every f sigma set, is a set of discontinuities for some function? But that can be covered a bit later. What we cover now is just what sets can be expressed as f sigma, that it can be written as union of closed sets, or some condition on that. So the statement is the following. Theorem. And I state very important part here, let MD be a complete metric space. Notice I use completeness here. If Gn is a sequence of dense open sets in M, then the intersection n equal 1 to Gn is, and that's, by the way, that of course is a G delta set. It's an intersection of open sets. So this G delta set is dense in M.
say one more time what density means?
Oh, good question. A dense set. So, what is a dense set? So, if I have A, it's a subset of M, is dense if A closure is M. So that means that this set it contains either all points of M or every point that it doesn't contain is a limit point. So it's basically touching, it's everywhere, it's touching almost every point. Where do you see dense sets? So if you go to Chinatown, that's a locally dense set. Locally because everybody you are near is going to be Chinese, right? If you are going to Brighton Beach, it's a locally dense set. Why is it locally dense? Because everybody there near you is going to be Russian. So either you are Russian or you are next to a Russian, right? That's why I don't live at Brighton.
Where do you live?
Where do I live? I can tell you this. I mean, I had an interesting story about where I live. Right? I once was in a car accident, and somebody sitting in my class is very happy about it. I apologize, but he was very happy about it because he works for the DMV. And naturally, he can do something for me, I can do something for him. And then he comes to me and says, you're familiar. You were in that and that high school, in James Madison High School. I said, yes. And you had this teacher. And I said, yes. So it turns out that not only was he my student and working at the DMV, he was also a classmate sitting in my high school in the same classroom with the same teacher, the same math teacher. Okay, so he's even happier. Next, he asked me for help to get the assignment later. And what it turns out is that I don't live near that high school anymore, but he lives in the same block, exactly the same block, right? Just pretty much like less than 5 minutes walk away from me. And the funniest thing is I had to fail him. Right, and then he of course wanted to, what do you call it, have drinks with me. I never I never went, but it's unfortunate. All right.
Question.
Right.
The closure of A.
Closure of A, yes.
Wait, so what were we talking
About closures, right? So you see, closure means that it's a set that is, well, we are saying A is dense if its closure is O of M. That means that A is such a set that it touches every point of M. Either it contains it or it touches it, okay?
Isn't the classic example the rationals and reals?
Yes, that's a good example. Rationals and reals are just a typical example. Rationals are touching every real number. They might not be real numbers, yes, exactly. So, good? Everybody understands what dense sets are. Right? We're going to let us say nowhere dense, locally dense, all that stuff. Locally dense I gave an example for, right? So, right? It's of course a relative property. What do you take to be your universe? What do you take to be the collection of elements?
Is it naturally closed?
Is a dense set naturally closed? No, Q is not closed in R. Right? It's something that if you close it, if you give it all the limit points, you are going to contain everything. Okay? That's how you think of dense sets. So if you take the closure of the rationals in R, you contain every real number. Correct? Good.
So can you explain just 1 second the F sigma set?
F sigma set, yes. What about it?
Can you just explain?
Go over it again. Guys, yes. So if anything is unclear, just stop me, and there's no point to keep going otherwise. What is an F sigma set? An F sigma set is a countable union of closed sets. Countable union of closed sets, F sigma. So that's where you have the word sum. In that proof, we showed why F sigma sets are useful, I hope, right? So we know that if I want to study discontinuities, the set of all discontinuities, every such set, is a countable union of closed sets. In fact, I can also make those closed sets nested. In this proof, they are nested. So if I find that the oscillation is bigger than 1 over n, any oscillation that is bigger than 1 over n plus 1 is going to contain all those points in this oscillation. Okay? And I proved that the set of oscillations of order 1 over n, this set is closed. Okay. Now, union of closed sets. Must it be a closed set? Finite, correct. But what about countable?
No.
No.
The rationals, right?
Rational is an example of countable union of closed sets, of singletons, in fact. Right? Rational numbers, just label them x1, x2, x3, x4, and onwards, and then take union of x1, x2, x3, x4. That's an example of an F sigma set that is not a closed set. So there are many, many more unions. So what you create is is called sigma algebra. You're going to study it in later courses, right? So it's useful in probability theory, and it's useful in you like sigma algebra, right? And it's useful in measure theory, and it's useful in analysis. Good. You understood this proof, guys, right? All right. So back to this theorem. So what we're going to prove is that the intersection of open sets, which by the way, is it open? Is a countable intersection of open sets? Is it open?
Yes. Countable intersection or you
Countable intersection. No.
Necessarily, because the countable union of closed sets isn't necessarily closed.
Right.
Numbers.
Right. So good. I'm finding out stuff about you. I said I'm talking about Baire Category Theorem, but okay. Right. So let's try to prove this. So the proof is really just a very simple picture. So what you do is, how do you show that something is a dense set? My goal is to prove that this intersection, which is not necessarily open, that it is a dense set. How do I show that something is a dense set? So that it means that every element in this metric space M is either an element of this intersection or is arbitrarily close to an element in this intersection. Right? So this intersection, it's touching almost every, not almost, it's actually touching every element. It touches every element in M. So here is the picture that we have. So we pick any element x. So pick x belonging to M. We want to show that the ball of radius delta centered at x intersection, let's call the set G delta, is not empty. So G delta is going to be this intersection. I just don't want to write it many times. Right? So we want to show that it's not empty. That's enough to show that x is a limit point of G delta, and therefore when I take the closure of G delta, it will eat the x. So how are we going to do that? Well, G1 is dense. It's a dense open set. G1 is dense in MD. So G1 intersection ball of radius delta centered at x. It contains a ball of radius delta 1 around some point A, and it contains the closure of that ball. So what I mean is, here is what I do. So we have an open set. You agree that the intersection of G1 and this open ball is an open set. Not G delta, G1. Just one of the open sets in this intersection. The intersection of a finite number of open sets is open. So what I do is, I do something like this. I pick this x and I pick some point A, and I pick a very small, let me actually draw it a little larger for the next picture. So maybe something like this. So this is delta 1. And I picked it small enough so that its closure is going to be part of this open ball. Okay? So this is going to be all part of G1. That's basically how open sets intersect. They intersect, they have at least a bubble, at least one open set there. So now G2 is dense in MD. So G2 intersection, this time ball of radius delta 1 centered at A, contains a ball of radius delta 2 at let's call this point, let's call this A1, and this would be A2. And it contains the closure of that ball. So the picture that I have in mind is something like this. So I'm now looking at this blue ball, and somewhere is going to be a smaller red ball. Now I'm going to select the diameters. So continue this process. Such that delta n goes to 0. And what we have is then a sequence of sets like this. Ball of delta 1, A1, it contains ball of delta 2, A2, and so on and so forth. And not only that, the closures are like this. So the closures behave this way. The implication is that, notice that ball of radius delta n of A, it belongs to G1 intersection all the way to Gn. It's part of that ball, and it also belongs into the ball of radius delta centered at x. Now what's going to be the limit? What's going to be the intersection from n equal 1 to infinity of those balls? And I notice I placed closure over them. It's going to be a non-empty set. Usually it's a point, but actually I don't know that those sets are compact yet, because I don't know if they are totally bounded. So, but the intersection will be a non-empty set. And this set is a subset of G delta. It's a subset of G delta, which implies that some x, or not x, so let's call it y now. Y belongs to the intersection of those closed sets, and y is an element of G delta intersect ball of radius delta x. The proof is complete. So again, let's just go over this. What's happening here? My goal is to show that the intersection is reaching into this open ball. Since this open ball was chosen arbitrarily, if I find that the intersection reaches into this open ball, it has x as its limit point. So what I do is I shrink the balls. I select one open ball, and inside of it I select another, and inside of it I select another, and because I'm using completeness, I know that the intersection of all those balls is not going to be empty. Something will remain. Intuitively, you think 1 point will remain. But because we don't know if it's what sort of space it is, maybe what we're dealing with is not a compact set. So then maybe more than 1 point remains. But definitely something will remain. And that something is going to be an element of the intersection of those open sets. All right. So here are the consequences of this theorem. Do you remember the statement? Can I erase it? Consequences. So consequence 1. Notice that in R, the intersection Gn of dense open sets must be uncountable. So for if the intersection of Gn is countable, say x1, x2, xn, we have by Baire Category Theorem that if I take G1 minus x1 and I union and then I intersect it with G2 minus x2, and I continue doing this intersection, that this is going to be dense. But this set, I omit from it x1, I omit from it x2, I omit from it xn. This set is empty. Okay, let's just see it again. So we have shown that the intersection of all open dense sets is dense. Now suppose that this intersection is a countable set. Let's say suppose that this intersection is Q. Suppose it happened that this intersection is Q. Then I can list the elements x1, x2, xn, etc. Now, is this set open? Is G1 minus x1 open?
Yes.
Why? What happens if you omit 1 point? What is this? This is the same as the G1 intersection with the complement of a closed set. So you're removing one point is the same as taking the intersection with a complement of a closed set. One point is always a closed set, remember that. Remove the point, it's like intersecting G1 with an open set. So this is open. Obviously then this is open, it's the same exact type. Why is it dense? If you take away a point from a set in R, then it can always just have it as a limit point. That's the only way you can be dense. Actually not true. But why is it still dense? If you remove the point x1, that point x1 was either part of G1 or was a limit point of G1. If it was a point of G1, it had to contain a full interval centered at this point. So this G1 still has access, still touches this point x1. Do you see this? Right? So by Baire Category Theorem, we must have that this intersection is dense. That's what we showed. It's not a simple theorem. Just go over it, try to prove it on your own, see if you understand the idea. But we have shown that it is a dense set. On the other hand, if I omit point x1, if I omit the point x2, I omitted all the points x1, x2, x3, xn. The set has to be empty. Nothing survives. By a show of hands, how many of you are with me still?
I have a question.
Yeah?
So this works for R. It seems like it could work for other types of spaces.
That's why I proved it in a general setting. It works for spaces where the spaces are complete. You understand? Because where did we use completeness? It's at this part that we use completeness, that the intersection of a countable collection of closed balls is a closed. Sorry, this intersection is not empty. That's where we used completeness. So this theorem is not valid for spaces that are not complete. So it's not valid for Q.
Okay. So, because I was just saying, you said like notice in R. So could you just say notice in complete spaces in general?
In notice in complete spaces in general, true.
Okay.
But one thing, well, almost true. I mean, one thing is take the discrete space, for example. Discrete space is deleting a point, you delete quite a lot. It's no longer dense. If you delete one point in a discrete space, you made a non-dense set.
So is there some other conditions like?
The conditions is that I mean, if it's true in Rn, right? It's true in spaces that are very similar or somewhat similar to R. What has to be true is, you see, when we do this construction, when we have this construction here, when we delete those points, deleting a point from an open set still allows this open set to have access to this point. It still has to be a limit point. So that's a condition. See? So any space, that's what we use here. Any space where deleting a point from an open space, from an open ball or an open set, does not result in this set no longer being dense. So that's a condition.
Question.
Yep.
Why not an R if you can use a closed interval?
Yeah, but what we use is, what we used in R is this. So in the picture, if I delete x1 and x1 is not part of G1, then I didn't modify G1. G1 stayed the same. If I deleted a point from G1, so if I deleted the point x1 now, that full interval was part of G1. So just removing one point, cutting out one point, still gives you access from this interval. You can still access this point. You can touch it from the right, and you can touch it from the left. So you still have a dense set. That's what happens in R. Yes? Wonderful. Those are very, very difficult theorems, very dense theorems. Consequences are just amazing. Just to imagine figuring out such a theorem on your own, coming up with it. You would get Fields Medal. So that's one consequence, is that such a set is uncountable. Consequence number 2 is in R, so Q cannot be written as a G delta set. Why? Now tell me why, somebody please.
Q is uncountable?
Because Q is countable. Q is countable. 1, 2, 3, 4, 5, 6, 7 onwards. Right? You can count Q.
So G delta set just means it's a intersection of.
Yes, G delta is intersection of open sets. So Q is not a G delta set. Q is not a G delta set.
So it's F sigma and G delta.
F sigma and G delta, right? And we're going to see what it means. So for Q not to be a G delta, that tells us something about continuous functions, or discontinuous functions, in fact. So Q cannot be written as a G delta set. Why? Because it's countable. Because Q is countable. Yet, and that's very important, yet every G delta, and I should put in R, be careful that you are not assuming that G deltas are uncountable. Every G delta in R is uncountable. Okay? But we're saying that in R, if I take intersection of open dense sets, I will get an uncountable set. I will never get a countable set. Never ever. So consequence that follows from it 3. Consequence 3 is, let me ask it as a question. Can df equal to can df be equal to R minus Q? Can it ever be the set of irrational numbers for some f from R to R? Why or why not? So think about it for a moment.
Because the rational numbers are uncountable?
Again, rationals are countable.
No, it's not.
Irrationals.
Irrational.
Yeah, that has something to do with it, sure, but careful.
G delta must be uncountable.
Exactly, G delta.
So F sigma must be countable.
No, F sigma does not have to be countable. That's not the point. So be careful, right? Be careful here. F sigma does not have to be countable. We have seen examples of F sigma that is uncountable. What is that example? Give me a function for which F sigma is uncountable. In other words, give me a function where the set of discontinuities is an uncountable set. Are there such functions?
Characteristic function.
Characteristic function, we just did it. So yeah.
Is it because, so an F sigma set is a union of closed sets?
Yes.
Right, if you take the complement of that, you get the G delta set, which would be uncountable, but it'd have to be the rationals, which is countable.
That's very good. Right, so let me just try to explain what was just said. So, if the F is equal to R minus Q, then R minus Q is a union of closed sets, or countable union of closed sets,
Just by definition.
by a theorem that we established, not definition, right? It's a very simple theorem if you understood what I mean. Once you think about it, you will see that it's pretty simple. So this is countable union of closed sets. Okay?
And the only closed sets in R that don't contain an element of Q are singleton irrational.
That's actually also not bad, right? That's not bad, but you see, we have to be really careful. You see, it's not a simple fact at all. It's only a simple fact if you follow through that very, very difficult explanation of Baire Category Theorem, right? So what happens then is this. So if this is so, then what is the complement in R? What's the complement of that set? That will imply that if I take this complement, what's going to be the complement? What's going to be this thing here? This is R minus Q. What's going to be this thing here? It's going to be Q. Because when we do complements, we do that relative to R, right? It's basically everything in R that is not this. So it's R. But what is this? So this is now the intersection of sets Gn.
Why is dense?
Well, that's a good question. Wonderful attention, right? So now this intersection is obviously a dense set because it's Q. But the question is, why is each Gn dense? We need to establish. Now each Gn is dense. Otherwise, the intersection isn't dense. So I'm just escaping it very quickly. Otherwise, intersection isn't. Do you see it? Okay, very carefully, guys. What do we know up to this point? So if I take, basically, if I was able to write R minus Q as a union of closed sets, then I can write the complement as the intersection of open sets. Now, the fact that this is Q means that this intersection is a dense set, because Q is dense in the real number line. Now, the question is, what can I say about each Gn? It has to be dense, because if Gn is not dense, the intersection is even less. You agree? Once you take intersections, you are cutting away points. You're cutting away the tentacles of this intersection. So it's not able to touch everything, but it's still able to get every Q, every rational number. So therefore, it's still arbitrarily close to any real number. That cannot happen if Gn is not dense. And now this is a contradiction, because the intersection of those sets must be uncountable. But according to Baire Category Theorem, or according to consequence 1, the intersection Gn must be uncountable. So you have to understand this. Okay, so it has to be uncountable. What we have shown, thus, there are no functions. Df equal to r minus q is impossible. It's impossible. Here is another consequence. So, consequence 4. If I can write R as a union En, where each E sub n is closed, then some En must contain an interval. Then some En must contain an interval. Do you see why this is the case?
R is uncountable.
R is uncountable, right? So what we're saying is that we cannot possibly write it as a union of closed sets where each closed set is missing an interval. Why that does happen? It's also, if you take the complement, you get the empty set. Now, the intersection of, that means that the intersection is not that of dense open sets. So if I just take, let's write Y. Why? Because if I now take the complement, I get that the empty set is equal to the intersection of En complement. And that is intersection of open sets. So it's an intersection of open sets. Now the question is, are those open sets dense? Are they dense?
Oh, if it was dense and closed, it would be R. Right?
No, I mean, dense and open, it would not necessarily be R, but it would be some uncountable set. That's the point. We not only get we don't even get that, we get empty. So these sets are not dense. At least one is not. At least one E sub n is not dense. E sub n complement, sorry, right? Which implies that E sub n complement intersected with some interval is the empty set. And the implication is that I is a subset of En. And the proof is complete. So they cannot all be dense because we got intersection is empty. If they were all dense, the intersection will be some dense set, some uncountable set in particular. Okay? So something went wrong. So that means, by the way, so something went wrong, sure, and that means that at least one of those sets contains an interval. Let's just ask a few more questions. So suppose that I found that this intersection of the complement is Q. Could that be the case? Could I have found that this intersection were, not in this example, but we had some closed sets. I didn't tell you what they are. And we had their union. I took the complement. Could the intersection be some countable set? No, couldn't be. It's impossible. We just already wrote it. Exactly. Neither Q nor anything countable is a possibility. Open sets do not intersect. Either their intersection is going to be not dense, or it's going to be dense. And if it's going to be dense, it's going to be an uncountable set. Could the intersection have been just a few numbers? 1, 2, 3, 4, 5. Just complements of closed sets, by the way. Right, so something like this, where it's a complement of closed sets. Could that intersection be finite?
Not the complement of open sets.
Yeah, that could happen, right? Just like it happened here to be the empty set, it could happen that the intersection is anything, but it could not happen if those sets are dense. Okay? Okay. So next consequence is just really the same as 4. Very similar to 4. 5. If R is the union of En, then, now I no longer assume that they are closed, then En closure contains an interval for some N. Yes, sorry? It did? Really?
But you can continue.
Really?
Want.
I'm so sorry, guys. Are you sure about it?
On such a roll, we didn't want to.
Oh my God. So go on.